Hey everybody, let's take a look at an example problem now. We've talked about trusses and frames and machines. So we want to take a look at, we're going to start by looking at trusses, and we want to learn a couple of things about how do we solve for the system of trusses. And so I've got a truss system up here. I basically stole this from an online catalog, shopping catalog actually. And so I found a truss that looks something like this. I know it's 36 feet from left to right, okay, and I know it's got a pitch of 4/12, which means that for every 12 inches I go over, I'm going to rise 4, okay, so basically 1/3, because we're going to use that 1/3 a lot here in a little bit. So here's 18 feet, so 1/3 of that is 6 feet, so this must be 6 feet over here. Now I've placed these pins, or the places where the beams come together, the members come together, at nice positions. So E and D are both 6 feet from A in the horizontal direction, symmetrically over here on the other side, and then F is 12 feet. That's probably not accurate as far as the actual dimensions of the truss that I found on the catalog. At least the pictures don't give me nice values like that, but I'm going with the nice values just to make my life simple. All right, and so there's our system. Right, there's our system. And what I'm going to do is I'm going to load it, and I'm going to load it with 400 pounds on these two left-hand positions at D and at J. Right, so I'm loading it with 400 pounds there, and I'm going to load it with 1,000 pounds at the pinnacle of the roof at H. Right, I could put more load in there. I'm just not going to, because I don't want to make it more complicated than it already is. And I've also made it 400 pounds on both the left and the right side, and 1,000 in the middle. The 400 pounds on both the left and the right side gives me symmetry. Now let's talk a little bit about that. The symmetry is a great thing, because what that does for me is it says, hey, whatever I do over here at the left-hand side, I don't need to do on the right, because once I found it on the left-hand side, the right-hand side is identical. So whatever I find member TEF has for a force, then TIL is going to have the same exact force. Okay, so symmetry makes my life nicer. If I were to load this with 400 and this with 800, then I've got to do what I'm about to do all the way across. I've got to solve that all the way across. And it's a lot of equations already, so let's not make this any harder than we actually have to at this point in time. All right, a couple of other things for convention. Whenever I look at a member like AC, I'm gonna go alphabetical. So TAC is the tension in member AC, and almost invariably I'm going to have the members under tension, and so they're not all going to be under tension, and we're going to see that with the very first equation set that we look at. But what that does is I don't have to think about it. I just make them under tension. The mathematics will give me a numerical value that's negative, which tells me that they're not under tension, they're under compression. But I don't want to have to think about that, right? So I'm not going to, right? So I'm going to do that in that fashion, okay? All right, so we're going to use what's called the method of joints. All right, so the method of joints basically says look at each of the joints on the truss. So A, C, D, F, H, G, E, right? I don't need to go any farther than that again, because of symmetry, the left-hand side will be the same as the right-hand side. So that'll be taken care of. Okay? Now, first things first. If I have these forces by some sort of a weight on top, or something's pushing down on top, we'll assume it's a weight of some type, then I also have to look at the support. So this truss is over, let's say a building, and there's a support here at A and a support here at B. All right, so there's a support at A and a support at B. I've put a pin support over here at A. I've put a roller support over here at B, just to kind of make life simple. So if I look at the truss externally, if I look at the external forces, then there's a force here at B, and then A has a Y component and an X component. But we can see from this diagram, in this specific situation, there are no other X forces. There are no other X forces. And so A sub X is going to equal 0. Could I put a pin there or over here? Yeah, then I'd have an A sub X and a B sub X, and there'd be no way for me to determine what those are. But it's easier just to put a roller here. In fact, they'd both be 0 because there are no forces except up and down, right? So anyway, let's leave that alone. So when I do the sum of the forces in the X, I get A sub X equals 0. And then the sum of the forces in the Y, I'm going to get A sub Y plus B minus 1,800 pounds equals 0, right? So A sub Y and B are unknown. Okay, so I need the sum of the moments, and I'm going to take the sum of the moments about A. In fact, let me get rid of the A sub X right now. And if we think about this already in terms of symmetry, it's pretty clear what's going to happen here. If I've got 1,000 in the middle, 400 on either side, so 1,800 down, these two on the sides, because of symmetry, should be 900. But let's do the moment equation just to make sure. All right, so the sum of the moments about A, of course, A sub Y does not supply a moment. I'm just going to call that A now. It doesn't apply a moment at A. And so what am I going to get? I'm going to get 400 pounds times 6 feet, right? Because it's 6 feet from here to here. And that's negative, right? That's going to be, if I hold the hinge at A, 400 pounds is going to try to rotate it in the clockwise direction. Also negative moment, also negative moment. So minus 1,000 pounds times 18 feet minus 400 pounds. Let's see. Minus 400 pounds times 30 feet plus B times 36 feet. And all of that's going to equal 0. Okay, so in the downward direction, here's 400 pounds times 30, 400 pounds times 6. So that's 400 pounds times 36. Right, so minus 400 pounds times 36 feet. I could use my calculator, I don't want to at this point. Minus 1,000 pounds times 18 feet. But 1,000 pounds times 18 feet is going to be 2,000 pounds times, it's going to be 500 pounds times 36 feet. Same thing, right? So this is 500 pounds times 36 feet. And I'm going to take the B times 36 feet and bring it to the other side of the equation. And you can see there's a 36 going to drop out of everything. That's why I did it that way. These all become positive, or I can put a negative sign out in front of the B. It doesn't matter, they'll cancel. And I get 400 plus 500 because the 36 will all go away. Right, that should be B. And that tells me that B is equal to 900 pounds, which of course the symmetry arguments gave me the same thing, right? So B is 900 pounds, that means A is 900 pounds. All right, so there are the forces acting on the truss as a whole. All right, so that's all I've done so far. Nice free body diagram, and then the forces on the entire system, and I've solved for the external forces at A and B. All right, let's hang tight for a little bit. I'll come back with another video here in just a minute. Well, you can get to it whenever you want. I'll come back with another video, and then we'll start breaking things down. All right, so if you have any questions on this first part of the problem, please leave them in the comments below. Thank you.